Recording. Okay, so we're recording now. I hope everybody can see the screen and also can see the screen of the iPad. So let's see what we're going to talk about. Let me just put something under the. So let me just put something under here. The trouble with the iPad is that when you lay it down on its back, it's got a bump where the camera is. Okay, so let me go back to the section that we were more. Let me get rid of this damn thing. It'll come back, of course. So let's go differential equations. So we were basically here, and I think we had finished that, and so we're up to the issue of separable partial differential equations. By the way, yesterday I wasn't aware, although I was aware maybe 2 months ago, but I wasn't aware that yesterday was a holiday, a UNM holiday, a collapsed form of a fall break. And so I held class anyway. A few of you showed up, and I recorded the session, and it's on the UNM webpage, the usual place where we put the Wednesday 468 classes. So you can look at it there, but I think I mainly answered questions about the homework. Anyhow, let's go on with our discussion of differential equations. Section 7.3 is about separable partial differential equations. So partial differential equations become much simpler when they can be converted into semi-independent ordinary differential equations. And that happens when you can write the function of several variables. I don't know why I can't get this to stay away. Write the function of several variables as the product of functions of single variables. And then the partial differential equation becomes a set of ordinary differential equations, one for each x. So we would have, in this case, n ordinary differential equations. And separability turns out to be sometimes it's related to symmetry. And in fact, symmetry shows up in a funny way in many cases. Often it shows up and we don't recognize it as symmetry. For example, the fact that the fields of quarks and leptons are complex. Well, that's because there are really two fields for each quark, and these two fields have the same mass parameter. So there's a symmetry there. In the case of equations, the equations of physics often are spherically symmetric, and so they involve a Laplacian, and the resulting partial differential equations, which I'm using the acronym PDE for partial differential equation, ODE for ordinary differential equation. These PDEs then are separable in several coordinate systems. So there are various examples here. And so I guess I'll go through some of them. Normally I skip most of the examples, but these examples are so important in physics that I thought maybe I would do some of them. So Poisson's equation, or Laplace's equation, is Laplacian of the electrostatic potential vanishes where the charge vanishes. In that case, it would also be Gauss's law. It's a second order linear homogeneous partial differential equation, and it separates in many coordinate systems. What you can do then is you can write phi as a function of x times a function of y times a function of z, and then this thing separates. Maybe I should in fact do that since that was the first example there. So let's let phi equal to x of x, y of y. Let's maybe make this visible, z of z. And then we have partial to partial x squared. Well, let me in fact change this slightly. So that on x of x, y of y, z of z, of course, it is equal to y of y, c of z, partial to x, partial x squared. So you can see then if you have Laplacian, which is sometimes written as just triangle of phi, what you will have then is yz x double prime plus xz y double prime plus xy z double prime, where the primes refer to derivatives and derivatives with respect to the independent variable, which is y in the case of capital Y, z in the case of capital Z. So this equation then is that the sum of these three things is equal to 0. And what you do is you divide by x, y, z. So you have Laplacian phi over x, y, z is equal to, well, then it's x double prime over x plus y double prime over y plus z double prime over z equals 0. Now this is just a function. In fact, maybe if I use colors, I might say this is a function of x. This one is a function, say, of y, and this one is a function of z. And the only way that this equation can be satisfied is if this one is a constant, this one is also a constant, and this one is a third constant, such that c plus c prime plus c double prime is equal to 0. So that's how one solves this. And so in this case, then, we get back to a sensible color like blue, we would have x double prime is equal to c double prime x. And so what could that be? Depending upon what c double prime is, you could have, for example, x equal to e to the So this is capital X, okay. E to the little x times the square root of C double prime, because then you'd have X prime would be square root of C double prime X, and X double prime would be C double prime X. And C double prime could be real, or could be positive or negative, or even complex for that matter. And anyway, those are the solutions. And so you typically have, in these cases, you have either growing exponentials like x goes as e to the x, y goes as e to the y, z goes as e to the z, or x goes as e to the ix, y, e to the I, y, and I. Oh, this is little y. Let me fix this. And z goes as e to the little z. So I'm leaving out the C double prime in this case. And of course, the primes and double primes on C are just mean different constants. Let me get my coffee. Oh, so remember we have this chat function. If you want to ask a question, say something on the chat function. Poisson's equation, which is Gauss's law, is that the Laplacian of phi is, this actually isn't Gauss's law. This is Poisson's equation for the electrostatic potential minus Laplacian of phi is rho over the electric constant. And so in this case, what we have is an inhomogeneous differential equation. And so it's a little more complicated than that. And it depends upon what rho is and so forth. But you can often separate it if rho has suitable symmetry. One can also use Green's functions techniques. In fact, that's what we described back in fact, I can pop back there, I think, and show you what it was. Let me just get rid of this. Back here in Laplace transforms and Fourier transforms, we talked about Laplace transforms and Green's functions. Right, here we are. So here's the way we can solve Poisson's equation. So here's Poisson's equation, and you see this is the standard way to solve it. In any event, going back to separable, damn this thing, separable partial differential equations. Of course, we have Maxwell's equations, and in empty space, they take this simpler form, and E and B then obey these wave equations, and these are separable in many different coordinate systems, rectangular, cylindrical, and spherical. And for example, the exponentials like this describe plane waves. In fact, light is described by plane waves like this. Another common equation is Helmholtz's equation. And if we're in 2 dimensions, rectangular coordinates, it looks like this. And so once again, we do something similar to what I showed over here. Namely, we just write f of x as x of x and capital X of x and capital Y of y. Now we can do this if what did I do here? Right, okay, we have the same f on both sides. So what we can, notice this is not the same as Poisson's equation. In Poisson's equation, we had phi here and then we had rho there. Here we have f on both sides. So Helmholtz's equation is much simpler. And so then we use a technique like this. We just set f equal to capital X, capital Y, differentiate, and we get this. Then we divide by X times Y, and we get two equations that one for capital X, one for capital Y, and they solve the original equation if a squared plus b squared is k squared. Just in case that's not completely clear, what we do is if we take this equation here and we divide by capital X, capital Y, and we get minus 1 over capital X, X double prime minus Y double prime over capital Y is equal to k squared. And now we know that this has to be a constant, and we're going to say that this is equal to a squared, and this one is equal to b squared, and so we have that a squared plus b squared has to be k squared. And then solutions are, for example, e to the iax, e to the iby, but you could have exponential solutions. You could have a and b real. Well, a and b are real in this case, but you could have cases like x is equal to e to the x square root of a, y is equal to e to the y square root of b, where a and b here are positive, let us say. And then as long as this equation is satisfied, you have a solution. So these can be growing solutions. They don't have to be oscillating solutions. One can do the same thing in polar coordinates. Then you just write f as capital rho, capital phi, and you go through the same thing, but it's, I mean, rectangular coordinates are really marvelous because everything is so simple, and x, I mean, if you've seen one rectangular coordinate, you've seen them all. X is like y is like z, everything's the same. Whereas in polar coordinates, you've got second derivative with respect to rho, 1 over rho, d by d rho, 1 over rho squared, d by d phi squared, so it's more complicated. But and you can do the same thing. You just set f equal to rho phi, divide by rho phi, and then you get this expression, and then you see that this has to be a function of rho, or all of this is a function of rho, and all of this is a function of phi, so this has to be a constant, and that has to be a constant. We set the two constants equal to n squared. And then there's something subtle that happens that is sometimes skipped in books, and it's that this n does not need to be an integer, but on the other hand, if you want the whole, in other words, here, let me maybe change colors back to, say, black now. If you want in the phi plane, so this is the phi plane, and you go around from 0 to 2 pi, if you want to avoid a cut or a discontinuity here, then in e to the I n phi, then what you want is n should be an integer. Because then e to the I 2 pi n is equal to 1. And so we get, which is equal to e to the I n 0, which is, of course, e to the 0 which is 1. So you need n to be an integer if you want phi n of phi, which capital phi n of phi, which is e to the I n pi, to be single valued on the whole interval from 0 to 2 pi. Sometimes you don't need to. In other words, you could be discussing a problem in which you're solving, let us see, which equation is this? This is Helmholtz's equation. You're solving Helmholtz's equation in a wedge. And you have different conditions here, and you're solving it here. And so here you're only interested in this restricted range of phi. Well, in this case, you can let n be an arbitrary number. It doesn't have to be real, and it doesn't have to be an integer. Okay, let's see. The chat thing is empty here. I hope somebody has a question. You know, you guys need to guide me to some extent, and so if you want, if you find these examples boring, then tell me to speed up. If instead you like them, well, tell me to continue with them. In any event, this equation, this left-hand side equal to n squared, this is a more complicated equation than the phi equation. And in fact, it's Bessel's equation. If we change variables a little bit, we let capital rho equal to Jn of k rho, sorry. Then you have a solution, and you have a solution because this is then the same as this once you change variables appropriately. And this is Bessel's equation. So what you have then is you have the product e to the Jn of k rho e to the I n phi. So notice the way this k, which, now where was k? K was originally here. It doesn't occur in the phi solution, and it just sneaks up on us in the scaling of the radial variable in 2 dimensions. In 3 dimensions, okay, so there was a question about 726. Well, this comes from that. If you set p k n of rho equal to Jn of k rho and just differentiate, you get this. So just as an example, let me try to do one of the terms then. So we have one of the terms is rho squared p double prime sub kn of rho. Now what would this be? Well, this would be rho squared, the d2 d rho squared of Jn of k rho. And if I'm not mistaken, then if we want to set x equal to k rho, which is then, oh, sorry, I need to make this visible. Let me move this over here. So then no matter what I do, that's visible, and I can move this damn thing out of the way. It's so annoying. So what we do is we rewrite this as k squared rho squared 1 over k squared d2 d rho squared Jn of k rho. And now we replace k rho by x. We have 1 over x squared d2 dx squared Jn of x. So that's the first term over here. And then you do the same thing for this term and that term, and you get this equation. So that's how you get 726 out of 725. And all the other examples are essentially the same. So if we go now to 3 dimensions, then, and we're in rectangular coordinates, well, once again, we have this, we feel nice and comfortable because we've switched to rectangular coordinates, and then everything is so much simpler. And we just have this equation here. When the Laplacian, we said f equal to x, y, z, Laplacian hits x, y, z, the d by dx squared just hits the x, the d by dy squared just hits the y, the d by dz squared just hits the z, and then the right-hand side is that. You divide by x, y, z, and then what you get are the equations minus x double prime over x minus y double prime over y minus z double prime over z is equal to k squared. This one here is a constant. Now, why is this stupid? These damn, God. I tell you, this software, they think they're all geniuses because they make a fortune, but I think they're jerks. Anyway, so we've converted using rectangular coordinates. Helmholtz equation becomes this, and now we see that this is a function of x, this is a function of y, this is a function of z, and this is a constant. And the only way this can be true is that if each of these is a constant. So this one, all 3 are constants. And so then we're back to the equation minus x double prime equals a squared x. And so this is for the natural solution there is e to the I ax. And then you see you differentiate once and you get IA e to the IAX. Differentiate twice, you get minus a squared e to the IAX, which is minus a squared x. Okay, so that's how that works. In cylindrical coordinates, it's similar. The Laplacian in cylindrical coordinates looks like this. The Laplacian sphere is in cylindrical coordinates in 3 dimensions looks like this. That was worked out here. And so we set f equal to rho of rho, phi of phi, z of z. And then we multiply both sides by minus rho squared over rho phi z, and we get this expression. And once again, this is a function of rho, and well, this is a function of phi, excuse me, and so this is only a function of phi, so we immediately can solve that, and we let that be e to the in phi. And again, if we want the whole from 0 to 2 pi to be single valued, then n should be an integer. So that drops out there. What we have left after this is a constant, we can then divide through by rho squared. And what we get is something in rho squared equals a constant. And that then is, it becomes this earlier equation, which was the lead up to Bessel's equation. In other words, it's this one. We get this equation, but we get it with, oh, now where am I here? Right, okay. You get it with k squared replaced by alpha squared plus k squared. Now you might say, where the hell did alpha come from? Oh, we said z equal to e to the alpha z. So after we divide through by rho squared and set this equal to n squared, then divide through by rho squared, this guy has to be a constant. And so we set it equal to e to the alpha z. And the equation looks like this. Now, if alpha is real, this is a growing or decreasing exponential. If alpha is imaginary, it's oscillating. And in either case, alpha squared is real. But notice that if alpha squared is negative and bigger than k squared, then this thing becomes imaginary. And then we have what is called a modified Bessel function. Okay. Now, of course, you're also, you may be more used to seeing Helmholtz's equation in spherical than in cylindrical coordinates. And in that case, we have, this is the Laplacian. We set F equal to R of R, theta, theta, phi of phi. Once again, if we have all of we said phi equal to phi sub m equal to e to the im phi, divide by multiply by r squared over r phi, r theta phi, and what we get is this. And we once again get this separated into a differential equation for theta, and that involves L and M. And it turns out that L has to be an integer, and M is an integer if you want it single valued on the whole region. L must be an integer if theta is to be single valued and finite on the whole region 0 to pi. And then you get F being a solution of Helmholtz's equation, as long as R satisfies the right equation. And it will, because if you set R sub KL of R equal to JL of KR, then you get this where JL of X is the spherical Bessel functions. Now, as I might have said to you earlier, the cylindrical Bessel functions are kind of nightmare functions because they're infinite series and they're kind of unfamiliar. But the spherical Bessel functions are very nice. They're related to sines and cosines in a very simple way. So the spherical Bessel functions are your friends. Now, why are they nicer? Well, they're nicer because they come from an equation that's more symmetrical than the cylindrical equation. Or to put it differently, if you have spherical symmetry rather than cylindrical symmetry, you're just much better off. You have nicer functions. In special relativity and in general relativity, the time and space coordinates are often written in this way, with upper indices, sometimes with lower indices. If they're written with upper indices, the normal convention is that x0 really is the parameter having to do with time, and x1, x2, and x3 are spatial coordinates. And then the inner product, if I'm writing it as px as x3 vector dot x3 vector minus p0 x0, or equivalently x dot x minus et. Here, I'm in units again with h bar and c equal to 1 because otherwise you just have to keep track of the h bars and c's, and it's a waste. It's in general a waste of time. I once met a more senior theoretical physicist. I think he was a theorist. Anyway, he was of the view that setting h bar and c equal to 1 was a dangerous thing to do, and it caused people to lose contact with reality in some way. He might be right, but I just can't go on with H bar and C. We just have too damn many factors, and all the equations are ugly. And the more complicated the equation or the sentence, the more neurons in your brain get used up keeping track of all these irrelevant things, and then you can miss the point. And so the simplicity of natural units is valuable for learning. And in my book, I didn't do that. In many sections, I put H bar and C into all the equations whenever I remembered to, and the result is the equations are more complicated than they need be, and I think probably that was a mistake. In any event, that's irrelevant to. Let me just mention the special relativity business because it comes up in electrodynamics as well as in other areas of physics. So it's x dot x minus et. And this is written as p lower a x upper a. This is Einstein's convention. And so this lower a, though, means that we have a minus sign on the time component. So p lower 0 is minus p upper 0, or minus the energy. X lower 0 is minus x upper 0, minus the time. And d lower a is the regular derivative. D upper a is different, you see. So d lower a means the derivative with respect to the ordinary coordinate x upper a, whereas d upper a is the derivative with respect to x lower a, and x lower a well, it can be, so this is actually wrong now that I think about it. If a is 0, then x lower a is minus x upper, d upper 0 is minus d lower 0, but for the spatial derivatives, it's not true. So this is actually a mistake here. So I need to correct that. I was sloppy there. Unfortunately, we have two metrics in use. One is P0x0 minus x dot x. That's the other metric. So some people, when they say px, they mean this. And this is particularly the case in particle physics, whereas in general relativity, this is the rule. And in particle astrophysics, well, it should be this rule. I'm not sure. Depends on the author. The Klein-Gordon equation. Well, Minkowski space just means flat space. The analog of the Laplacian, again in natural units, looks like this. And so what we get is the Laplacian minus d by dt squared. So here I'm doing the right thing. I just was sloppy in the earlier equation. And so just as triangle can, well, this is not so bad. Just as triangle can represent the Laplacian this way, a box can represent the four-dimensional relativistically invariant Laplacian. So in the Klein-Gordon equation then is box minus m squared. It looks like this. Again, we're in these units. If we set a of x equal to b of a single variable, so this is four variables here, x0, x1, x2, x3. This is just one variable, px. Then the kth derivative of a, which is the kth derivative of b of px, is just pk times the derivative of B with respect to Px. And so the solution of the Klein-Gordon equation then is just P squared minus P0 squared B double prime minus M squared B. And so we just get this. And so just as long as B double prime is minus B and P squared is P vector squared minus P0 squared, you have a solution of this equation, namely a P squared plus M squared equals 0. And then you satisfy the Klein-Gordon equation. This condition, P squared plus M squared equals 0, means that the energy is related to the mass in this way. And so this is just ordinary special relativity. So let's see, we've got some more examples here. I don't know how many of these examples I should go through. Some of these are more associated with particle physics. Maybe I'll just go through them very briefly. And if there's a question, send me a chat right away. For a spin zero field, like for example, one of the components of the Higgs field, the quantum field looks like this. This annihilates a particle of momentum P. This is a spin zero field. This creates a particle of momentum P. And these A and A dagger satisfies these canonical commutation relations. Notice they're at equal times. They follow from these equal time commutation relations. There are no time variables in the annihilation creation operators. The photon, which is of course, maybe I should do this example a little bit. In the electromagnetic field has 4 components, but one quantizes. In quantum field theory, in the gauge theory, we first fix the gauge and then quantize. And one of the nice gauges is called the Coulomb gauge. It's also called the radiation gauge. And it's at the divergence of the transverse part of A vanishes. That means that the time component is a function of the charge density, and the vector potential in the absence of charges or current satisfies this wave equation. In any event, the electromagnetic field can then be written this way. This annihilates a photon of polarization S, and there are 2 possible polarizations, basically this way or that way. And this creates a photon of momentum P and polarization S. And then there are these polarization vectors. These polarization vectors are orthogonal to they are 3 vectors, because this is a 3 vector, and 3 vector P dot 3 vector E vanishes. This respects the Coulomb gauge condition that divergence of A is 0. These A and A dagger obey these commutation relations. S assumes 2 values here, so you have delta SS prime. But because we've got this funny condition here that we've got these vectors, these are 3-dimensional vectors, but we only have 2 polarizations. The result is that the canonical commutation relations involve what's called a transverse delta function. And so they look like this. In other words, for an ordinary delta function, you wouldn't have this term. With this term, you have the transverse delta function. That way, you satisfy the radiation condition. Dirac's equation is, it's basically gamma A times the 8th derivative plus the mass is equal to, acting on a, let us say, Majorana field is 0. And so it satisfies this Dirac equation. The gamma matrices have an anti-commutator that's twice the metric of flat spacetime. And what's cute here is that if phi of x is any four-component field that satisfies each of whose four components satisfy the Klein-Gordon equation, then if you operate on phi with this differential operator, you get a solution of the Dirac equation. The simplest Dirac field is a Majorana field. If you have Majorana fields for the two Majorana fields with the same mass, then you can form a Dirac field. And incidentally, these anti-commutation relations, in particular, this one tells you that you can't put, this is the Pauli exclusion principle. In other words, what it says is a dagger of PS times a dagger of PS is equal to 0. And so, for example, if you had a state, any state psi, this would be a dagger of PS on a state that has one Dirac particle or Majorana particle momentum P and spin S plus whatever else is in the state. And if you try to add a second one, you get 0. And so that's the Pauli exclusion principle. This Pauli exclusion principle is probably the simplest principle to understand and the most important physical principle, one of the very most important. I mean, the whole structure of atoms and molecules is a consequence of the Pauli exclusion principle. Otherwise, all the electrons would pop down to the n equals 0 state. So let's see. The next topic is first order differential equations. So now that's the thing about differential equations, which is kind of unappealing. Namely, I know of no overriding general principle that describes the whole field the way analyticity describes complex variable theory. So it's almost like every differential equation has its own theory. So we have to consider many special cases. And of course, we're discussing the simple cases, namely linear and low order. So for example, you have this equation, dy dx is some function of x and y, and we can write that as a ratio minus p over q. And so people write it this way. This is called a first order ordinary differential equation. It's ordinary because it's not partial differential, partial derivative. There's only one independent variable, one dependent variable, y. First order because it's first derivatives. Now, these things are easily solved if they're separable. And a separable first order equation is one in which this thing here can be rewritten as f of x dx plus g of y dy. So then it's, then we say that this equation is separable, and so this equation is separable, and this is its separated form. Once you have the separated form, you just integrate over x and over y, and you still get 0. You integrate from x0 to x, from y0 to y. And what do you wind up with eventually? Well, eventually you've got two constants, x0 and y0, and you've got a function involving x and y and two constants, and you solve that as a function y of x, and so you get then a solution. Then let me just say 7.59 imply. Well, that's in my notes. I may have different numbers. This then says that y is some function y of x, x0 and y0. So what we get is a first order, you get a first order differential equation that's separated. Another way of thinking of it is that, well, actually, I don't know if that's a way of thinking about it. You can, let's see. No, I guess there's no use doing that. Here's an example. I'm going to skip this example at the moment and go to an example that's a little more relevant, and maybe come back to it if you want to see it. It's related to supersymmetry, but it's more general than that. It's related to quantum mechanics. Anyway, in 1913, Auerbach noticed that many quantities are distributed in a particular way, and they're distributed this way. In other words, we've got a bunch of items, cities, names, people, charges, bills, whatever. And we order them according to some rational order. And then the deal is that typically dn is minus a dx over x to the k plus 1. And if k is not 0, we can solve this, and we find that n plus c is a divided by k x to the k, or rewriting it, we get this expression: x is a over k n plus c to the 1 over k. So this gives you the value of the item that has rank n. So that's what this thing is. So the value of the nth item in the list is typically like that, where a and c are suitable constants. And what he noticed was that the case k equal to 1 occurs frequently. And in that case, if k is equal to 1, we have that x is just a over n plus c. And we can go further and just set c equal to 0. And then we have that, so let me just go to that particular case and maybe change colors. In that case, if we have k equal to 1 and k equal to 1, then x is equal to a over n plus c. And this is called Zipf's law. And with c equal to 0, in which case x is equal to just a over n, it applies approximately, let me just write that as a over n, to the population of cities. So if the largest city has population x, the second one will have x over 2, x over 3, x over 4. And this again is approximate, obviously, and it depends on the country and how many cities and so on and so forth. I never checked that. But there's another case that shows up, which is, again, with k equal to 1 and c equal to 0. And it occurs to numbers in a table. So the number is x, and n might be the number of times that the number occurs in the table. And we call that the rank of it. And so the rank n is then a over x, simply because, because x is equal to a over n. So this is fairly simple. So then you might say, well, suppose these are numbers. For example, they might be the deductions on Trump's tax return. which of course we're never going to see until after the election. Possibly not then. So then the rank of number x is n is a over x, and so the number of numbers that occur between that occur with first digit d and 4 trailing digits would be n d000 minus n d999, which is to say a over d000 minus 1 over d9999. Well, that's really a over that. And you rationalize it and you find out that it drops quadratically with d. And so the first digit is much more likely to be 1 than 9 by a factor of 45. And in fact, the German government uses this formula and others like it to catch people who cheat on their German taxes. I don't know if the IRS has caught on. Of course, the IRS, Trump has decimated the IRS. Hardly anybody working there these days. Another important first order separable separated equation is the logistic equation. Dy dt is ay 1 minus y over some capital Y. This describes many different things in nature, and it's more common and more I would think it's a little more accurate than Zipf's law. In any event, you can solve it. You let little f equal to little y over capital Y, and then the equation becomes f dot, let's say df dy is this, and you can then solve that this way. And so let's see, d by dt is often written as dot. I think this started by Newton. And so we can rewrite this. So in other words, what we have here is, let me shift to maybe blue again. So what we have there is df dt is equal to af 1 minus f, and so we write that as df over f 1 minus f is equal to a dt. And this thing integrates to, of course, at minus some, what did I write? I called it th for some reason. And this one we can rewrite using this equation as df over f plus df over 1 minus f, and this integrates to log f plus, or actually minus. So let me, which is to say log f over 1 minus f is equal to a t minus th. And then what you get then is this expression here. And what does that look like? Well, it's, what it looks like is, so let's see, let me just write it as f is equal to e to the a t minus th over 1 plus e to the a t minus th. And so then what is this? Well, if you go to, let's see, this very last part isn't very clear. So let me write this as t minus th. And so if you go to log negative t, this one is essentially 0. Log negative t, we're just getting something that's 0 over 1. And so it's essentially 0. If we go to large positive T, we see that the thing goes to 1. So roughly the thing looks like this, where this is TH, this is 0, and this is 1. This is called a sigmoidal shape. And it applies to a great many things, especially in biology, but undoubtedly many other ways. Gell-Mann, who unfortunately died a couple of years ago, but maybe 5 years ago or 10 years ago, he would teach a short course on complexity at UNM, and it was great fun listening to him because he was so smart and had such wide knowledge and experience. When I could, I would sit in his class and ask questions, and I would particularly try to ask a question that would get him on a tangent, because tangents were just absolutely fascinating. Because he had so much intelligence and so much experience. I think I'm going to skip 2 of these examples and get on to something called hidden separability. But if you want those examples, then send me a chat and I'll go back and do them. Or I could do them on Wednesday's 468 class. So suppose we have these functions P and Q in this ODE. So we've got an ODE here, P dx plus Q dy equals 0. But suppose you can factor the 2 of them into U of x and V of y and R of x, S of y. Well, then what you do is you just divide by R of x, V of y, and you get this expression. And now the thing is separated. You integrate both sides. And notice that when you do integrate this, so let me just quickly switch to say back to red. If you do integrate this, what you do is you're integrating from x0 to x, U of x prime, R of x prime, dx prime plus integral y0 to y, S of y prime over V of y prime, dy prime. Actually, I think this, I would say that this in fact is equal to 0. So I'm just wondering whether I was sloppy in 7.80. So what instead, in my book, you get is this integral is some function of x. So call it, call it f of, it's some function of x and x0, plus over here some other function of y and y0. This is after you've done the integral, and this is equal to 0. So this gives you an equation, y is equal to y of x, x0, and y0. So it gives you a solution that depends upon 2 independent constants that you've chosen to be the lower limits of integration. So another example of hidden separability is in this case, we divide, well, so once again, the coefficients are factored. And now, of course, you can have these coefficients, P and Q, and if you see them as a function of X and Y, it might not be obvious that you can factor them into a function of X times a function of Y. So that's not always obvious. But if you can, and then you divide like this, you get this, and you integrate, and you get this equation here. Here I've written C. I've lumped the lower limits into C. So now this thing has jumped back to an earlier. Let me make this big again. It's jumped. In fact, I can even make it bigger. It's jumped. All right. Anyway, so you get this, and then you find that y is 1 plus c x squared minus 1. Now, here's an important concept that I guess first occurred like in this part of the differential equation theory, but then has propagated since then into many areas of mathematics and physics for that matter. So we say that a differential equation is exact if this left-hand side, this thing here is really d phi. In other words, this is the differential of some function of x and y. So in other words, it's the x derivative of phi plus times dx plus the y derivative of phi times dy. In other words, so let me quickly shift back. Maybe I'll go to black. What we're saying here is that p dx plus q dy is equal to something partial phi partial x dx plus partial phi partial y dy. In this case, the thing is said to be exact. And the nice thing about exact first order differential equations is that one can often integrate them. In fact, I imagine we can always integrate them. These, let's just look at what the criteria are of exactness. It's namely that P, if P is partial phi partial x and Q is partial phi partial y, then partial P partial y, which is partial phi partial x partial y, is equal to partial q partial x. And so that's this is then this is called the condition of integrability. So this is the integrability. I paused there because when I was in grammar school, I was changed from one school to another. And I left the first school before they taught spelling, and I entered the second one after that school had taught spelling. So I never really learned to spell. And one of the things I love about computers is that it corrects my spelling, or if it doesn't, I can ask Google to find me the right spelling. In any event, so this, if we have this condition of integrability, then the ODE, the ordinary differential equation, is exact, and we'll see that it's integrable. In particular, if a first order EDE that is separable and separated looks like this. This is exact because the y derivative of p is 0 and the x derivative of q is 0, so they satisfy the condition of integrability. Examples of such things are, these are two amusing examples. Maybe I can just mention them quickly. One is Boyle's law. We have PdV plus VdP equals 0. It's exact because PdV plus VdP is the differential of PV. And the integrated form is the ideal gas law. A more accurate formula was invented by van der Waals. This is kind of interesting though, so maybe I should mention it. B prime is the volume occupied, the effective volume occupied by a single molecule. And so you have to subtract from the volume of the molecules. Get rid of this damn thing. And then over here, we have A prime. If A prime is positive, then there's, this represents the mutual attraction of the molecules. So that means that you need a little less pressure in order to satisfy this equation. So let me just check whether A prime is actually greater than 0. I may have gotten the sign wrong. In any event, it's A prime is real, let's put it that way. And if they were charged, I guess they'd repel each other. So in general, it's real. This equation by Van der Waals, which he probably produced in the year, I don't know, 1857 or 58 or so, 1860 maybe. It was a sign that molecules were real particles. Physicists were enamored by the partial differential equations of acoustics and then optics after Maxwell, and electrodynamics after Maxwell and Faraday explained electrodynamics. And so they looked down upon the chemists who were talking about atoms and molecules, and they thought it was, the physicists thought it was just sort of mumbo jumbo and kind of bookkeeping. But then in 1905, Einstein related the viscous friction coefficient and the diffusion constant, both of which could be measured, to the energy of a thermal fluctuation by this expression. So given these two, and given that you can measure T with a thermometer, you get that a measurement of what the Boltzmann constant was. And so all of a sudden, bingo, everything became real. Chemistry was then accepted as an actual science. Human population growth, well, okay, you can read that example on your own. The meaning of exactness, well, we've only got a couple of minutes. I will mention this quickly, and then I'm going to do this again on Tuesday. Basically, we can integrate this differential along any contour. But what do we get when we do that? What we get is a function that depends upon the contour in general. On the other hand, if this is the differential of something, then the integral of that differential depends only on the endpoints. And so that's the huge difference. This is very much like complex variable theory, where you can, where the contour integral of an analytic function depends upon the endpoints and not upon the contour chosen. So it's the same kind of thing. And so that's basically that's the meaning of exactness, and mainly that you can, that when you integrate this equation, you get a function that depends upon the endpoints of the contour and not upon the contour itself, the details of the contour. And so if you have, then you do the integral and you get B, that gives you a function that gives you that phi of xy and x0, y0 is some number B. And this then is the solution of the ODE, because once you've done this integral along some contour, you've got some function B that's just a function of x, y, x0, and y0. And you can then solve that equation for y of x, x0 and y0, and b, but b is just a function of these. And so you get the solution. So that's basically how that works. So there may be a question, so shoot me a chat question. We've only got a minute left, but it's certainly time for a question, and I can go longer with the question. Here in this example, which I think I will do next time, I show how you can actually use exactness to solve the differential equation, although probably I think there must be a simpler way of something simpler than my example 7.19. So we're basically out of time. Does anybody have a question here? On the website, I added another set of homework so that I'd avoid leaving you guys with nothing to do. But go to bars and catch COVID, the new coronavirus. All right, I'll just end the thing if there's no question. So have a nice weekend. And as I said, this is a very dangerous virus. And in fact, I think on the class website, I'm going to put a link to an editorial in a very recent issue, the most recent issue of the New England Journal of Medicine, an editorial about the coronavirus. And I think it's worth reading, especially the first couple of paragraphs and the last paragraph. All right, so I'm going to end it now. So goodbye, everybody. Have a great weekend. So,
Thank you.
Thank you. Have a good weekend.
Thank you.
Thank you very much.
Okay, thank you. Stop share and